Assalamu alaikum everyone. In today's lecture, we are going to perform the steady state heat thermal analysis. And there are three problems we are going to practice, but 3-1, okay, this is heat transfer Unisys Angel. And I will solve example 3-3, okay, using the Ansys. And I will leave the rest to 3-2 and 3-1 to you, okay. This is approximately a 1 hour activity, and okay, let's start. Okay, you see that, okay, this is a composite wall here, and the boundary, okay, you see that the side layers are made of glass and the middle layer is basically the air. Okay, that's basically the double glass window. And okay, so how we can do that? Okay, just start that. Okay, go to the Ansys, okay, and look for the steady state thermal analysis. Just drag and drop to the project area. Okay, first we need to consider the materials here. There are two different materials. The first one is the glass and the second one is the air. Okay, so look at that. Okay, the thermal conductivity of the glass is given as 0.78, and for the air it's 0.026. so first of all, I will select the engineering data. And here the default structure material is static structure, but I can define another material. Okay, but if I go to the engineering data source, you can find the air as well. Okay, you can just add the air from here, or you can just define a new material. You see that, okay, now the air is here, but you see that the thermal conductivity property of the air is different. Okay, or if I select the air, okay, it's 0.024, but here it has been defined as 0.026. so to change that, okay, now it's taking the data from the source. Okay, I can just click here and then I can break the link to the source. So anything the properties defined in the source or the Ansys, that can be delink using this option. So now I can change the value here like 0.026. you can directly do that as well. Okay, that you can also you can just write 0.026, that will be also fine, but I just delink the air, the material from the Ansys library, and now the property is 0.026. okay, and the second one is the glass. So I can just add the glass here, and for the glass there is no property here, so just select the glass here and then select isotopic thermal conductivity and then include the property here. And for the glass, the property thermal conductivity is 0.78. okay, you see there. Okay, I'll just check the unit. Okay, watt per meter per degree Celsius or per Kelvin, these are the same. Okay, you see that, just check the here. Okay, air and the glass. Okay, you see that there is no source library or the source file here. So you see that, okay, when I these two are, you can say that now the similar. Okay, so I can just import the material, add the material from the library as I did with the air. Okay, and then delink that, so that's same as like defining a new material. Okay, that they are the same as you can see here. So now I have defined the material, just close that, and now I need to like create this geometry here. So there is 4 mm, 10 mm and 4 millimeter. Okay, you see that if for the flux, okay, if I need to determine the flux, which is basically the heat transfer per unit area, then the width of this wall doesn't matter. Okay, only the thickness matter. But I will calculate the heat transfer here, or the different the temperature at the inner inner walls as well. So how we can do that? Okay, let's see that. So just okay, this is the design bottler. First I need to know what's the dimension of this rectangle here. So you see there is 0.8 meter high and 1.5 meter wide. Okay, so click XY plane, look at, go to the sketching, select the rectangle here. So okay, just let me change. Okay, just zoom in using the mouse, and that's 1.5. okay, that's fine. Okay, now make sure I'm just coinciding one vertex with the origin, so it's P here. Okay, that's fine. go to the dimensions, general, okay, specify the length, specify the width. So it says 0.8 meter high and 1.5 meter wide, so 1.5 here and 0.8 here, as you can see that. Okay, so I need to now give it a thickness, so that's in millimeters, so I will change my unit to millimeters and just start extrusion. And for that I need to select the sketch first, so select this sketch, apply, and okay, and then the thickness is 4 millimeters, so I will define the thickness 4 millimeter and then generate. Okay, so now I have glass, okay, this area, and now I need to define the air. Okay, so there are two ways I can do that. Okay, so I will show you first the easy way. Okay, for that I need to create a plane here. Okay, to draw the sketch on this surface I need a plane here. So using the surface face filter, I would select this face, go to the new plane, and then okay, this is the plane, and then generate. Okay, now I have this plane, and then look at, and for that that's an easy way. Okay, so just draw a rectangle and go to the constraint. Okay, now these must be coincident. Okay, these edges should be coincide with this glass edges. For that go to the modeling, go to the sketching, constraints. So I will select the coincident, this should be coincident with this one, this must be coincident with this one, this should be coincident with this one, and this should be coincident with this one. Okay, now all these are coincident. Okay, and I have my sketch here, and now I need to extrude that for 10 millimeter. So just select the extrusion option for the sketch, just like this sketch, apply, and thickness should be 10 millimeter, and then generate. Okay, now you see that, oh sorry, I forgot. Okay, for this extrusion option, okay, so if you select the operation to the add material, so it would just add material to the previous one. Okay, that it will not treat that as a separate body. Okay, because they are the same material, but as you see that in our case these two materials are different, so in that case we need to change this operation option to add frozen. Okay, so now the Ansys will treat these two as different bodies. Okay, you see that this is a different body. Right now you see that there is just one part, one body. So if I click the generate here by selecting the add froze, so you would just see that these are the two different bodies that you can see here. So I've written it for you here as well. Okay, so it creates a new body even if the extrusion strap overlaps with the previous added body. Okay, now I need to create a third body here. Okay, on this side. Okay, so now the previous one was the easy way, so just perform another practice, which is basically you can see that the projection method. So for that, okay, I need another plane, so just like this surface, new plane. Okay, so I have created this plane. Okay, now okay, the plane is here. Okay, at this surface, so just right click, insert, and then there is an option of sketch projection. This option we have utilized before in you know the simply supported beam as problem as well. So just select sketch projections and select this. Okay, select this face, apply, and then okay, this is the sketch. To create this sketch, okay, just write generate. Okay, now Ansys will, you see that it will create a sketch. Okay, new sketch. Okay, by tracking the, you can say, the edges of the bottom surface. So now I have this third sketch. You can do it in the same way as you have done with the extrusion to sketch as well. So just select the extrusion option, and for this one select this sketch, apply, and I need the 4 millimeters here. So click on generate. Okay, now you see that I have 3 parts and 3 different bodies. Okay, so you can just zoom in here and you can see that. Okay, these are 3 different bodies, 1, 2, and 3. The middle layer is basically the air. So now I have created this geometry. Okay, just I want to save this file. Okay, so let me create a folder at the desktop. Okay, you can say that composite wall. Okay, you will do the same for exam. Okay, just keep in mind. Okay, so I will save this geometry for future analysis. Okay, so just go to the file and then export, and at the desktop, okay, there is file, where is that, composite analysis. Okay, the composite wall. Okay, this is one, and I will save it as a step file. So composite, you can say that wall, or you can say that double pane window. Okay, so now I have saved the step file of this geometry. Okay, I can reuse it for further analysis. Okay, so just close the design modeler. Now start Ansys mechanical. Sorry, I forgot. Okay, did I check the add froze option for the third one? I don't know. Okay, let me just check that, what I did with the third extrusion. I guess as there were 3 bodies, so everything should be fine, but let me confirm it again. So I will reopen the design modeler. Okay, as there are 3 bodies, I guess this should be fine. So if I go to extrude option, extrude to, so just change that. Okay, add material to add frozen. Okay, just change that. Okay, because those are the different materials. So I have these 3 different materials. Okay, 3 parts. Okay, just I will close the Ansys. Okay, so first I need to assign the materials for all these bodies. Okay, so I will go to the geometry imports option here. Geometry for the first solid. Okay, it's glass, so just specify the glass here, and for the second body it was air, the middle layer was air, and the third one was also glass, so I will select the glass here. Okay, for the mesh, just select the mesh here, and then okay, you see that okay, these are the 3 different bodies. Okay, so you see that there is a third option, which is basically the contacts. Okay, it defined the contact between 2 surfaces. So by default, okay, Ansys define the contact type as bonded. Okay, which is same as you see that these 2 surfaces are closely you can say that closely joined, or you can say the welded. So that's why you can see the surface here. Okay, it's the contact region. Okay, and these 2 surfaces. So it defines these 2, first, second, and then the third and fourth. Okay, and for the mesh size, okay, just click here and update. Ansys will automatically create the mesh. Okay, see that this is a coarse mesh. Okay, if I want to, you can say that refine it a bit. Okay, so just go to the sizing, and then you see that there is an option of resolution. Okay, right, by default it has defined resolution of 2, so you can just increase it to 4 or 5 to get a finer mesh. Okay, so just generate mesh. You see that the mesh will automatically refine. Okay, so now I have a finer mesh. Okay, now I need to define the conditions. Okay, boundary conditions here. So first one is, you see that this is a convection condition. Okay, because this is between the air and the window, and here you see that the H value defined as 10 watt per meter square, and the inner temperature, the temperature of the air inside the room is 20 degrees Celsius. So for that, go to the steady state, insert the convection condition here, select the surface, apply, and these are the watt per meter square. Okay, watt per meter square, that's fine. So this is 10, and the temperature is 20, I guess. So I will define the temperature as 10. So 10 and 20. Okay, for the outside temperature, that's -10 and 40, because outside, okay, the air is not stagnant. Okay, it has a higher value, so you can say that it's windy. So just select the convection condition here, just rotate that, select the surface, apply, and here I will need to define H value, film coefficient 40, and the outside temperature is -10. Okay, so I have defined the boundary conditions here. Now I need to define the solution parameter. First I need the temperature profile, and then you can say that the heat flux, okay, the total heat flux or the directional heat flux. As you know that since I have selected the boundary condition only along these surfaces, okay, this one and this one, so it Ansys will automatically get these surfaces as adiabatic surfaces, okay, which I have not defined any for, which I have not defined any condition like this one and this one, so that's fine. So there is no need of directional heat flux, so both these two will give the same result. So I will select the total heat flux here, and then I guess that's fine. Okay, that's what I'm required. So I will say solve. So I have my temperature profile here. You see that on this side, okay, on the surface the temperature is about 14.2, okay, on the glass, okay. You see that the air temperature is 20 degrees Celsius, and T1 value is approximately 14.2, and the glass value inside that's about -8.55, okay. And if I go to the solution here, you see that, okay, first of all the heat transfer rate, it's 69.2, okay. So if I divide this one with the area, so I would get the value of 57.6, so which is basically the heat flux. So Q dot divided by area is 0.8 multiplied by 1.5, so I would get 57.6. So if I select the total heat flux, you see that this is approximately the same as 57.6, okay. But if I want to know, okay, how much heat is getting transferred, which is basically here heat transfer rate 69.2. So for that I have two options, since I have defined the convection conditions here. So if I can just select it here, drag it from here to here, and then I can determine, okay, this will determine how much heat is passing through this surface, okay, this convection, okay. And for this one I can just drag and drop here, just drag and drop, okay. So you can just select and drop here, and then evaluate all results. You see that, okay, so if I select the 69.2 probe on the inner surface, you see that the value of heat passing through this surface in a unit time is 69.19. So from the book the value is 69.2, so these are almost the same. And on the outer surface, okay, you see that for the probe 2, okay, convection 2, and this was convection 1, so the convection 2 is also minus 69.19, okay, at this surface, okay, because you see that, okay, heat is getting transferred, okay, at this point heat is you can say that inward, okay, there is a transfer from high temperature to low temperature, okay, in this direction. But from this surface the heat is going to be like emitted, so that's why the value is negative here. So in this way I can just validate my result, okay, the heat input must be equal to the heat output. So you can either just drag and drop here, or you can just select insert and then select the probe, and then you can select the reaction, and now you can define the convection boundary condition at which you want the heat transfer rate. So convection 1 or convection 2, so that would work the same. So evaluate all results. So you see that, okay, that's 69.19, okay. So both way you can select this reaction probe. Another thing I want to determine is basically the temperature at the interface of the air and this glass, okay, which is basically T2. So how I can do that, okay, you see that for that, okay, let me just close it, okay. One thing is you can use the probe here, and you can get the approximate value. Where is the probe? First select the temperature profile and then go to the result, and then I can select the probe here to determine the temperature, okay, approximate temperature at the interface. But there is another way, okay. For that, okay, I will define another condition, okay. I will suppress, you can see that this is solid 3, solid 1, okay. I would suppress this solid 3, which is basically this outer green surface. So I would just suppress that, suppress body, okay. And now I will define another condition, another solution value like temperature at this surface, okay. Sorry, just select the surface, and then what's that, temperature to apply at this surface, okay, that's fine. And then evaluate all results. Oh sorry, don't forget to unsuppress the body, okay. Now I have defined the value at the interface. Okay, in the same way, okay, you can suppress these two bodies, and then you can define the temperature at the junction of these two surfaces, okay, to get the temperature value. So you see that, okay, at the interface, how much temperature do I have? That's 13.93, and okay, the book didn't evaluate it, okay, it's 14.2 here. So no, that's at the outer surface, and the inner surface, okay, T2, which I have calculated, it's 13.93. so you can validate these results using the Ansys workbench, okay, that's fine. Sorry, using the theoretical calculations. I hope you get that, okay. In this way, now you have done the convection part, and for the conduction you can solve this problem by yourself. I wanted to solve this problem, okay. This is 3-2 by yourself, and 3-1, okay, you have to do these two problems by yourself. If you have any question, you can ask in the class. Thank you. Allah Hafiz.